The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so today I'm going to talk about formaldehyde, the S1, S0 transition. This is a beautiful example of simple is good, because when you look at a simple problem, you can analyze it to death and then be surprised. And the surprise is incredibly important in teaching you something about the fundamental behavior of molecules. And so in this case, we're going to go through and predict everything there is to predict about the transition from the ground state of formaldehyde to the excited state, using the kind of information that's either available or that you can guess. And we are going to be surprised because we're going to see something that appears in the vibrational structure of this transition, which is unexpected and leads us to evidence that the excited state is non-planar. There's a low barrier to planarity. And so even though the structure of the excited state is non-planar and would therefore require not using C2V, we use C2V and we see staggering in the vibrational structure associated with the out-of-plane bend, which is a universal signature of tunneling through a barrier. And that's a universal signature of whenever you have a low symmetry form, it's almost always associated with a kind of level staggering associated with tunneling through the barrier to the high symmetry form. And this appears again and again in different forms. And this is, I think, one of the first and clearest examples that taught us a huge amount about what to expect and how to assemble the pieces. So let's begin. The first thing we do, I should say that formaldehyde, this transition in formaldehyde was the first polyatomic molecule electronic transition that was rotationally resolved and assigned. And it was done in 1934, 25 years before the second one was done, which was acetylene. It's a little bit surprising because the ground state of formaldehyde is an asymmetric top. It's a prolate top, near prolate top. It has a relatively small arotational constant. So the different K levels are populated at the temperatures that were available to Kistiakowsky and Dickey in the 30s. They didn't use liquid nitrogen for cooling, or at least they certainly didn't use a supersonic jet. Although Kisti was one of the first to attempt to do a supersonic expansion, and it didn't work. And it's surprising that the idea for doing supersonic jet cooling survived Kistiakowsky's null experiment.
I think the problem was vacuum.
Yeah,
speed, yeah.
It was. But I mean, when a famous person does an experiment and it doesn't reveal the effect that you expect, there's a lot of dead time before someone else comes in and does it.
Well, I think it was about 30 years.
That might be. So anyway, the problem in formaldehyde is that a vibrational band consists of many different K stacks, and it's also a molecule that has 6 vibrational normal modes, and so the spectrum is going to be pretty busy and at relatively low resolution. This is pretty hard to do, and in addition, the transition is nominally forbidden They didn't know that. Maybe they did, maybe they didn't. And so it's relatively weak. So it's kind of heroic and surprising that formaldehyde, not acetylene, was the first.
Does
But
the large A constant give you resolution, help with the resolution?
it helps. I mean, the resolution of in the 30s, they had big spectrographs. I don't know how large the spectrograph that Kisiakowski used, but it was fairly common to have multi-meter long spectrographs. And so resolution of a few hundredths of a wave number was possible. Acetylene being close to 200 nanometers made it a little bit dicey, whereas formaldehyde being in around 350 nanometers made it a lot easier. But anyway, this is a historic molecule. It began polyatomic molecule electronic spectroscopy. And so we want to just approach the molecule the way Kisti or somebody like Kisti might have done. Kisiakowski, I was a TA in his course, one of the last few times he taught it. He was a white Russian. That means he fought against the communists.
His brother was a red Russian.
Yeah, well, I didn't know that. But anyway, he was a really amazing character, not particularly likable. And anyway, he was also a science advisor for Eisenhower. Anyway, so Kisiakowski. So the first thing we want to do is look at the electronic structure of formaldehyde using the kinds of techniques that you would do without a big computer. Because I still believe that it's instructive to attempt to formulate a simple picture for the electronic structure using atomic orbitals and linear combinations of atomic orbitals and the minimal picture, because often you get a lot of insight. And of course you can always do something more, but you should know what you're expecting. So what do you know? On page 2 is a correlation diagram, and it's a really clever kind of correlation diagram. Over on the left is oxygen. In the middle is formaldehyde, and on the right is CO plus 2 hydrogen atoms. Why would we do this? Well, we do this because we know something about the electronic spectrum of CO and O2. But what relevance does O2 have? Well, if you take the 2 hydrogens and stick them into the C, that's the united atom O. And so if you then look at the orbitals on O and destroy the cylindrical symmetry, it's got spherical, oxygen in O2 has cylindrical symmetry. If you destroy the cylindrical symmetry, the relevant orbitals will split qualitatively in the way that you expect for this. And for CO plus 2 hydrogen, you have the electronic structure of CO to which you're going to attach 2 hydrogens, and you have to figure out where would the hydrogens want to be attached, and you can figure that out. So I think if I'm going to get through this lecture, I'm going to have to skip the correlation diagram argument. And so, but you should look at this correlation diagram, or this building up principles, and see how all of the steps in going from the 2 limits towards towards formaldehyde are justified. I mean, on the left-hand side, you have, the tricky thing is always, what happens to pi u and pi g orbitals, both here and here? Now, it's not really legal to put G and star, and it's not legal to put U and G on heteronuclear orbitals. But basically, you have orbitals that are perpendicular to the plane, and orbitals that are in the plane, and you classify them. And then you ask, well, which one is going to be more stabilized by the breaking of the symmetry? And then there's another thing you do, and that is you ask, well, what is the IP of hydrogen versus the IP of CO? The reason we do this is we want to place the orbitals relative to vacuum correctly. And so the IP is always known. And so it turns out that the ionization energy for hydrogen is a little bit less than the ionization energy for CO. And so that means that the hydrogen orbitals are less stable than the HOMO in CO. And that helps you to figure out, well, what are the hydrogen atoms going to bond to? And so you do all of that stuff, and you end up with predictions of the relative energies and shapes of orbitals. And the goal is almost always to find out, for the molecule you're interested in, what is the highest occupied molecular orbital and its symmetry, and what is the lowest unoccupied molecular orbital and its symmetry. And sometimes the orbitals aren't completely filled, but usually, especially when you don't have really high symmetry and you have an even number of electrons, the orbitals are filled up to the HOMO has 2 electrons and the LUMO has 0 electrons. But sometimes it's a little bit more complicated. Okay, so we're in a position to begin predicting what you expect. And so, I mean, I love to do this, but I think that if I do this, I will be laboring something which is least important and most familiar to all of you. So I'm going to just write down what...
Where did the diagram come from that you have?
Hertzberg.
Okay.
And it is from Hertzberg, and I see I don't have the right page. I don't have the page given, but okay. So we have the highest occupied and the lowest unoccupied orbitals. 2b2 and 2b1. So, and both of these are related to pi orbitals on the both oxygen and CO. And so these labels came from looking at the planar and out-of-plane forms of the pi bonding and pi antibonding orbitals. So this is a pi star, an antibonding orbital. And so the HOMO to LUMO transition corresponds to, well, first of all of the orbitals up to the HOMO are doubly filled, and so the ground state is singlet A1. In C2V, the totally symmetric state is A1, and so the excited state is predicted to have the electronic symmetry B2 times B1, which is A2. So we expect that the excited state, if it is C2V, will be singlet A2. Now, why should we expect it not to be C2V symmetry? Two things. You have an antibonding orbital here. There's two ways that molecules respond to an antibonding orbital. One is the carbon will change its hybridization and so that it will take the antibonding orbital and tip it away from the other part of the antibonding orbital on oxygen. And so you go from sp squared hybridization to sp cubed hybridization. And that will change the angle here, and it will tip the hydrogens relative to the plane. And it will point the orbital, which would have been perpendicular to the board, has to be in sp squared. And it will point it in a direction, instead of 90 degrees to the bond, 109 degrees to the bond, and thereby diminish the antibonding interaction. So you can use Lewis ideas and change the hybridization. Or you can use Walsh type ideas, and you can say, we have an antibond, and we'd like to take that antibond, or the antibonding orbital on carbon, and get the hydrogen atoms involved with it. Well, the antibond, the pi orbital, this pi orbital has a node in the plane of the molecule, and the hydrogens are, by definition, in the nodal plane. So if we pull the hydrogens up out of the nodal plane, they can start to have a bonding contribution from the antibonding orbital. And more importantly, that polarizes the orbital out of the region between the carbon and the oxygen. So these are two completely different but equivalent outcomes, and they have to be, I mean, they're really the same. It's just two different languages. One is in the language of Lewis structures or valence bond theory, and the other is in the language of Walsh diagrams. So it is highly likely, regardless of which picture you choose, that this molecule will be bent. And so it will be not planar. You expect that the hydrogens will be out of the plane, and that the angle will be reduced from 100, well, it's actually 121. It should be 120 in sp squared, to reduce to 109, and it is reduced to 109. So everything about the structure that you infer from rotational constants is consistent with the molecule not being planar. Now there's another thing you can do. So you expect it to not be planar, and if it's not planar, then you're supposed to go to the lower symmetry, and you classify the vibrations in the lower state and the upper state in this lower symmetry. And you're supposed to then magically make predictions. And that you could do that. What do I want to say? Okay, there's more evidence. From the A, B, and C rotational constants, you can calculate the inertial defect. For the ground state, the inertial defect is very small and negative, which is what you expect for a planar molecule, because the A, B, and C rotational constants are not the equilibrium A, B, and C constants, but those for V equals 0, where already you have a little bit of amplitude, 0-point amplitude out of the plane. So, and you expect when that occurs to get small and negative inertial defect. For the excited state, the inertial defect from A, B, and C is larger by roughly a factor of 10 and positive, and that's conclusive evidence unless there's some kind of perturbation for a non-planar structure.
What do you mean unless there is some kind of...
I mean, when you have perturbations that you don't know about, the rotational constants, the vibrational constants are distorted from their isolated state values.
So one could imagine a planar excited state in which some perturbation makes it appear to rotational spectroscopy as if there was a out of plane.
Yes. If you have Coriolis interactions between two electronic states, all of the rotational constants can be changed, depending on what the mechanism is. And so the spectrum naively would look like a non-planar molecule, even though the molecule has a planar equilibrium structure. But the evidence is pointing to formaldehyde. You expect the excited state to be not planar. The A, B, and C rotational constants tell you it's not planar. And so then you say, okay, well, let's ask what do we expect about the vibrations, because you have two different point groups, and we classify the vibrations in CS and in C2V, and we get different qualitative patterns that where do I have? So you can do the group theory, and you can construct a reducible representation for the excited state. Well, you can construct a reducible representation by putting 3 Cartesian axes on each atom and then removing translations and rotations. And so you do that, and you get 3A1, 0A2, 1B1, and 2B2 vibrations. And this is the same thing you get for the ground state. You know, C2V, you have the same naming of modes. And so if you go to CS symmetry, these are, whoops. If you go to CS symmetry, you have 4 A prime modes, and you have 2 A double prime modes. You can do the group theory. So these 4 modes are totally symmetric, and this symmetry is the symmetry of the out-of-plane bend. And so the out-of-plane bend in the excited state, well, which is not planar, so it's the mode that takes you towards planar or through planar, becomes just one of the totally symmetric modes. The 2 non-totally symmetric modes are the 2 hydrogen WAG and the antisymmetric stretch. So there is clearly going to be something distinct about the nature of the vibrational transitions that you could observe if the molecule is behaving C2V-like versus CS-like, because this mode is going to behave differently in the 2 limits. And that's where the whole argument focuses. So what do we expect? We know how the geometry changes. We have an antibond, and so the CO stretch is going to be weaker. It's going to be reduced in frequency. So the CO stretch is nu2, and that'll be active because there's a fairly substantial change in the stretching frequency. The scissors, it's a planar motion, but since the hybridization changes, you'd expect the scissors to at least be a little bit active. And there's the outer plane, and you expect, regardless of whether you're supposed to be working in C2V or CS, you expect the out-of-plane bend to have some kind of activity. Whether it's a totally symmetric mode or a not totally symmetric mode, that's going to be the key. And let's see, did I get them all? I did. The symmetric CH stretch is seldom active in almost any molecule electronic transition, but it could be weakly active, especially if the CH bond gets a little strengthened by interaction with the antibonding pi star orbital. So you could have a little bit of activity in the CH stretch, but generally CH stretches in electronic transitions are pretty silent, because the Frank-Conan factors are really small for a change in quanta because of the nature of the oscillator. So there are these three modes that are expected to be active, nu 3, nu 4. And so you go and you look at the vibrational spectrum, and you find that, now remember, I said there's a way of numbering the normal modes. I now have found where it is. It's A before B, 1 before 2. You go through and G before U, and then you do B, and so on. So that you number, you start with the highest frequency mode, and that's within a symmetry, and you start with the first symmetry. And so the CH stretch is nu 1, and so there's an unambiguous way of labeling the modes, combining qualitative arguments and group theory. And so anybody without any great cleverness will be able to predict the nature of nu 5 for any molecule. And that's really amazing. Okay, so the vibration, what is observed in the spectrum is long progressions, well, progressions in CO. And they're progressions built on one quantum of the scissors. So in other words, you have a progression plus one quantum of the scissors. And so two progressions. And you have a progression plus one quantum of the CH stretch, really weak. And you have a progression involving something that's associated with it by process of elimination is related to the out-of-plane mode, and that thing has a frequency of 824 wave numbers. Now this is a smaller frequency significantly than all of the vibrational frequencies in the ground state. Now, when you go from the ground state to the excited state, the CO stretch decreases a lot. It goes from 1746 down to, where is it? 1182. So that's a big decrease. But an antibond isn't going to cause a big decrease in anything else. An 824 is already alarmingly small. And the alarm bells should be going off saying, what is this 824? And then there's the question, is this nu 4 or 2 nu 4? I mean, this is already small. Yeah?
Why are you saying that 824 is so alarmingly small? You know, looking at the table of the ground state frequency, so the decrease in the CO stretch is more than the decrease in the out-of-plane bend going from the ground to the excited state.
Well, but the problem is that there's a reason the CO stretch should decrease. An antibond is going to affect the CO stretch. It's not going to affect anything else. Well, maybe you can make an argument that the change in hybridization will cause, but there's no antibonding, and you know, so, and I haven't gone through the arguments. I mean, you have to ask, well, is a particular deformation going to be more or less favored in SP squared versus SP cubed? And that has to do with the fact that p orbitals are not flexible and s orbitals. So the argument is doable. I haven't gone through it, but I doubt that there's any sensible argument that could explain a decrease of 30% or 40% in any of the other frequencies. And so 824 is alarming, but the logic says if the molecule is somehow, even though it's not planar, obeying predictions from C2V, then 824 would have to be 2 quanta. And if, on the other hand, it's not planar and the analysis is done in CS, this could be 1 quantum. But then there's another thing. If it's really CS, why isn't there a long progression in this big change in geometry? Why is there only one 824? Why isn't there 1650 as well? There isn't. So there's, you say, this is a conundrum. We see 824, and it's too small, but it's actually maybe twice as small as what it seems to be, and nothing makes sense. So what do we do? Well, what we do is we think, and we analyze more carefully and ask, well, what do we expect? So if we are in C2V, the excited state, the S1 state, has A2 symmetry. And that's a forbidden transition from the ground state. So we cannot, well, it's forbidden by electric dipole. It's allowed by magnetic dipole. The general rule is forget magnetic dipole. Magnetic dipole is automatically a factor of roughly 1,000 or maybe a little more weaker than an electric dipole transition. So magnetic dipole is normally too weak to observe, but it could conceivably be observed. And it turns out it has been, but that's not it. So we have to then say, well, maybe this is what's called vibronically allowed. And so there are two flavors of non-totally symmetric modes in the S1 state of acetylene, formaldehyde. I have this problem, acetylene, formaldehyde. I've done so much work with both of them that, you'd think I would have a partition, but, it slips over. Okay, so we have, I forgot, what were the symmetries? We have B1, and we have B2. So the out-of-plane bend has B1 symmetry. The in-plane wag and the antisymmetric stretch, they have B2 symmetry. And all we need is for this product to contain one of the electric dipole allowed transitions. And so this will give rise to a state of B2 symmetry, and this will give rise to a state of B1 symmetry. And a B2 state corresponds to the B irreducible representation. So we expect rotational transitions that are B-type. And this B1 state, vibronically B1 state, will correspond to transitions that are C-type. B-type, delta K A of 1, delta K C of odd. C-type, delta K A of 1, delta Kc of even. So remember now, both of these could have a change of Ka, and you have two asymmetry components which have the different values of Kc. And so the higher energy component is always the one where Ka plus Kc is equal to J. And so one can always tell by assembling a level diagram from knowledge of the lower state energy levels and combination differences. You can find whether you're observing transitions that are upper to upper or upper to lower, and that provides you with a clear piece of spectroscopic evidence of whether the transition is vibronically allowed via a B1 promoting mode or a B2 promoting mode. This mixes in an electronic state of singlet B2 character, and this one mixes in an electronic state of singlet B1 character. And so the rotational structure, observed carefully, tells you which of these two vibronic coupling mechanisms it is. And it turns out that in formaldehyde, there are all three mechanisms: magnetic dipole, this vibronic coupling mechanism, and this one. And they all have different rotational structures. The magnetic dipole is A-type. And the strongest is this one. So the other two, there's a beautiful paper by Stu Strickler. He used to be at the University of Colorado. And he's one of these very quiet guys who do a couple of things really, really well. And one of the things that he did really, really well was to understand the electronic spectrum of formaldehyde. Anyway, so he observed and discusses all three types, but we're just going to focus on this one. So there's this mechanism which is clearly operational, and basically we know what's going on. We know that if we have a vibronically allowed transition from the ground state, we cannot see the V equals 0 level of the S1 state. Now, if I'm skipping too many steps, you should ask me questions, because this is really beautiful. And so we know that when you have a vibronically allowed transition, you have to have at least one quantum of what's called the promoting mode. And so the lowest vibrational level that we're going to see in cold band spectra will be to one quantum of the B1 vibration. So 0, 1, this is the B1 vibration. And there's then this A24 or whatever it is. Is it A24? Is it A24, A64? It doesn't really matter that much, but A24. We have this interval. And is this 2 or 3? Okay, if the molecule must be thought of as C2V, this is 3 quanta. If it's CS, it could be 2 quanta. But if it's 2 quanta, why isn't there 3? And why isn't there the 0 point level? So there may be some other things that I've stepped over. So what happens is you look at the spectrum carefully, and by becoming familiar with the rotational structure of a vibrational band, you can assemble things into a level diagram. And what happens is there is a hot band. And so if you look at the hot band structure after some analysis, you see a level diagram that looks like this. So this is the ground state, and so this is the overall V double prime equals 0 level. And this is V4 double prime is equal to 1. And then we have 2 levels, and so we observe a transition to this false origin, and that we're just going to call that frequency A. And there is another transition, which we know is from this hot band because that hot band has been observed in the infrared spectrum. This level has been observed either in the infrared spectrum or in a microwave spectrum. We know it's rotational constants. And so we do an analysis. We know this level is V equals 1 of the out-of-plane bend in the ground state. And this frequency is A minus 1280. And we know that this is 1167. So this is the vibrational frequency in the ground state. This is a transition to the A state, and it's shifted from the false origin by 1280. It's originating from here, and so you can conclude that this splitting is 113 wave numbers. Okay, so there's something a little fishy about this. This level is at A minus 1280 plus, okay, 1167, which is equal to A minus 113. Okay, so that's right. So we have A, it's a transition into this level. So it's A minus, so the energy, of the A level, okay, the energy of the A level, of this level is this frequency A, so this is the observed frequency. I'm sorry. Everything is right. I just can't say it. So this analysis requires that this splitting between 0 and 1 of the out-of-plane bend is 113 wave numbers. A completely ridiculous. If we were bothered by 864, or 864 divided by 2, this 113 is really, really a problem. But it's not a problem. It's the answer.
I'm sorry, what are those upper levels?
So these 2 levels are in the X state. And these 2 levels are in the A state. Okay, so this is a transition into the false origin. It's the lowest frequency cold band.
And that's the 4-1?
That's the 4-1 level. This is a hot band, and it's a transition which is, I think this, I can see this analysis now, right? Okay, and so this is from V equals 1 of the out-of-plane bend into a lower level. and you can calculate.
Okay, so the top one is 401 and the bottom one is 410.
Right.
Okay.
Okay, so now this is bothersome because now what we do is we construct a level diagram for the bending mode, the out-of-plane bending mode, and what we find is that, first of all, this lowest interval, now in these level diagram, there are transitions that change k. And so there's the A rotational constant being added and subtracted in here. And so, whereas over here, I've taken all of that out. And so this is 124 wave numbers, not 113 when you've corrected for A. And going from here to here is the 824. And then here's another level, 417. So, and 407. So here we have a level diagram, and this is for one vibrational mode, and you see a small, then a big, then a small, then a big. And it's what you expect for a double minimum potential with a relatively low barrier. So if you're way below a barrier, you expect that the left and right symmetric and asymmetric combinations are going to give rise to two levels close together, tunneling doublets or inversion doublets. And then if you go up higher and you have levels in the left and levels in the right, they're going to be separated by more because they tunnel, they feel each other. The tunneling rate is faster. The tunneling time corresponds to the reciprocal of the energy difference. And so this tunnels slowly, this tunnels fast. And so you expect a level diagram with a kind of staggering small, big, small, big.
Sorry, can you say again what tunnels slowly and what tunnels fast? I was writing down when you...
Okay, when you're far below the barrier, it's hard to tunnel because the tail of the wave function in the forbidden region is small.
Right.
There's little overlap. And so the tunneling splitting is going to be small. That corresponds to a long time.
Okay.
And as you get closer to the top of the barrier, the splitting gets bigger. This is always true when you have two or more non-symmetric structures that are that communicate with each other over a barrier.
What happened right at the top of the barrier if you had a state that was...
Well, this is pretty close to what we have in formaldehyde. So
what sets the limit for the size of that splitting?
The size of the splitting. Well, actually, it's easier to think about it this way. What do the energy levels look like for this potential versus this potential? These two wells are half as wide as this big one. And if you double the width of a well, you make the frequency half as large. And so one of the things that happens is once you're above the top of the barrier, it looks as though you're in the symmetric well. And so the sign of there being a barrier to the high symmetry disappears once you're above it. All that happens is this barrier causes a little bit of extra amplitude to accumulate in the region above the barrier, but even that is forgotten as you get up higher. So what is going on here is that we have, now where's the, John Brand did this. And John Brand, he was, who was the other, John Brand and Jerry King were two of the early polyatomic molecule electronic spectroscopists. They are different people, and one studied formaldehyde and one studied acetylene and other things. Brand was also interested in triplet states. So what he did, and I don't know, any of you know Rob Lipson. Rob Lipson more or less replaced John Brand. Okay, so there is this double minimum. He was able to fit the energy levels to a model, and he showed that the top of this barrier okay, so this is 650 wave numbers, and the 0 point level is 400 wave numbers. So you have a level, the lowest level is very, very close to the top of the barrier. And so that explains why the splitting is quite large as far as barrier penetration is concerned. So this, where did I had 124. So the first splitting is 124, and we're still below the top. The next level is above the top of the barrier, and it's starting to approach the expected structure, but with a wide potential. And now there's some terminology. This is a bent molecule. The 0 point level and the first excited state are both below the top of the barrier. When the 0 point level is near or above the top of the barrier, it's called quasi-planar. Because it resembles planar, but the quantum chemistry would get the structure not planar. It's just that there isn't anything in the spectrum that remembers that it's not planar, except for a little bit of level staggering as you go up. And so you get small, large alternation for a two-fold barrier. For a three-fold barrier, the structure involves threes rather than twos, and I don't remember quite how it works. But when you have a methyl rotor, you have a barrier to internal rotation, and the levels go A, E, E, A. And okay, so the answer to all of this is very simple, that the molecule is C2V here. The molecule remembers that it's C2V. The potential has minima that are not C2V, but there's two of them. And so you have this tunneling staggering in the energy levels, which is something that then prepared us to deal with much more complicated situations. But this was the first case where it was completely killed. And so I guess I'm probably over time, right? Not too bad. So at the end, I added a little bit of stuff that shows how you use the rotational spectrum, A, B, and C type spectra, to distinguish between magnetic dipole, vibronic coupling via B1 promoters, vibronic coupling via B2 promoters. They're all distinguishable, and they're all observed in the case of formaldehyde.
When you say B1 and B2 promoters, are you talking about vibrational state?
Yes.
Okay.
It's a little bit tricky whether you refer to the vibrational state or the electronic state that lends its character. And since we had A2 times B1, also the convention for vibrations to use lowercase. I'm not too observant of that, but it is.
So it's hard to speak in lowercase.
That is true. Some people can do it.
If you end up in that state, is that called a B2 promoter or a B1 promoter?
This would, I believe this is called the B1 promoter, but
But the symmetry of the total state is B2.
right. And so I don't know technically which is the universal way of specifying it. You can always say there's a B1 promoting mode and the electronic state, the vibronic character that has been borrowed. Yes. There are a lot of really beautiful things that you can deduce from really simple ideas about, well, which vibronic mechanism ought to be strongest based on how far are you away from the state that you borrow intensity from, and something about the coupling. And I'm going to talk about that next time. And beyond that, I don't know what I'm going to talk about, but I suspect there's some interesting topics before we quit. Okay, so I'm done.